In this video, we'll walk through an elegant approach to procedurally generate nodes in a radial widget such as a skill tree. This method is data-driven and scalable. We'll write blueprint code which generates a skill tree entirely from a data table, because the data table will contain the parent-child node relationships. The benefit to a data-driven design like this is it allows for the most rapid iteration during development. Instead of needing to open up all sorts of blueprints and change things in many places in our game, losing time and risking bugs and desynchronizations, with a data-driven design, whenever we want to add a new skill to our game, we need only open the data table and add a row. Another useful benefit of data tables many developers aren't aware of is they can easily be exported and imported into Unreal Engine from spreadsheets, allowing for even easier iteration. And lastly, and most importantly, using a data table will highly benefit our ability to design blueprint code, which will procedurally generate a skill tree for us based entirely on the data alone. So in our content browser, we're going to open up the Skill Tree Pro folder, go down to MISC Data and create a structure, right click, go to Blueprint, down to Structure, and we're going to call it S_Skill Tree Node. So this structure is going to represent one node in our skill tree. Each node is going to have a lot of data in it, but for now, we're only going to put one variable. We're going to call it child nodes. Make it a name array, save. Close it, and now we'll create a data table based on that structure. So right click, go to miscellaneous data table, find that structure, S_Skill_Tree node, okay, and we'll call it DT_Skill Tree. Open it up, and from this data table, we're going to procedurally generate all of our nodes in a skill tree based only on the information of what is the node's name and what are its child nodes. So for now, in here, we'll create a very basic layout for a skill tree just to kind of test our procedural generation. So we'll create one base node in the center, and then 4 nodes in the first layer, and then a couple nodes branching off of one of those nodes in the second tier. So let's add the base node. Under row name, we'll call it base. And let's add the 4 first tier nodes surrounding the base, and we'll call it UR for upper right, LR for lower right, LL for lower left, and UL for upper left. And we want to make these nodes children of the base because they're all going to be coming off of the base. And so to do that, we'll click on the base and we'll add 4 child nodes, and we'll give them the same names, UR, LR, LL, UL. And now let's say off this first node on the first tier, we'll have 2 nodes coming off of that. So we'll add 2 more, and we'll call it URA and URB. We'll add them as child nodes to UR, URA, URB. So now we have all the data we need to procedurally generate our skill tree with a base node, 4 nodes coming off the base node in the first tier, and then 2 nodes coming off of one of those nodes. And once we open up our WBP skill tree widget, the first thing we can do is delete the temporary nodes that we placed last time because we're going to procedurally generate them this time. And we can come over here to the graph. We're going to create a new function, call it generate nodes. Go back to the event graph, add it in. And this function is going to do all of our procedural generation. It's going to procedurally generate all of our nodes on construct. We'll add it to a category, call it procedural tree generation. We can also add this function to that category, and we might as well put this in a category as well, put it in setup. And now inside the generate nodes function, we're going to have one function for now, which keeps calling itself. And that's going to be called add node branching. So we'll go back to the generate nodes function, add it in, connect it, open it up, and we're going to add 3 inputs. The first input will be called node, second one parent node, third one parent node location. These 2 will be names, and this one will be a vector 2D. And in the node here, we're just going to make its default value base with a capital B. Now that we're done testing out this function, let's move it back over here, connecting this behind the catches. So it catches everything, then sets the appearance, and then generates the nodes so everything works properly. And here in the add node branching function, we're going to do two things. We're going to calculate the node location, and then we're going to add it to where it needs to go on the node canvas of the skill tree. So let's create a sequence, and we'll create a new function. We'll call it calculate node location. And another function, call it add widget to nodes canvas. And we'll put these both in the procedural tree generation category, as well as the add node branching. And we'll go back in the add node branching function, and we're going to call both of those, calculate node location, add widget to nodes canvas. Open up the calculate node location function, and let's add some inputs and an output. We're going to input the node and the parent node. And we're going to output the node location, which is a vector 2D. So back in the add node branching function, we could just connect it like this, but we're going to do a lot in this graph and it'll get pretty messy. So instead we'll right click and type node, scroll all the way to the bottom, and you can see the function parameters down here. So this is this, and you can do the same thing with parent node. And we're going to create a local variable off of this node location. So right click, promote to local variable, and we're just going to call this node location local. And we can comment this, call it calculate node location. So now we'll open the function back up. So how do we procedurally generate the nodes? We're going to be doing some procedural math here where we determine where to place nodes on a canvas. And because it's going to look like a radial skill tree with nodes branching out from other nodes, the information that we need in order to know where to place a node is where is its parent node, and also what are its sibling nodes, or in other words, what are the nodes in the same group also branching off from that parent node. So the first thing we need to do is get that information, get the node's context, find out its parent node and things like this. So we've passed the parent node in as a parameter here. So we're going to get that parent node, which is this again. And we're going to say if it's not equal to nothing, that means that if it is something, if it does have a parent node, in other words, if it's not the base node of our graph, right click, get data table row. And we could just select our DT skill tree here, but we probably will want the ability to create different skill trees. So let's make that a variable, right click, promote to variable, and let's make it private and put it in the category node generation. It's also kind of a clusterfuck over here because we forgot to put these variables into categories, so let's put them into sensible categories as well. Now that our variables are looking a bit more sane in the categories, we'll input the parent node here. And now this is something that trips a lot of people up. When you try to use a variable into this get data table row, you have this wildcard output. A lot of people think, oh, I can't use a data table as a variable in Blueprints. But that's not the case, because if you drag off of this and break to the particular struct that you want to use, in this case S skill tree node, and then compile, it becomes what you need it to. So now in this child node array, we're going to find ourself, the node, and we're going to promote it to a local variable called node index local. And the reason we're doing this is so we know which node in the array sequence is this node of its parent node's child nodes. So for example, is this the first child, the second child, the third child? And we need to know that because we need to know where it's going to spawn in the skill tree. If it's going radially, is it up here at the top, over here, down here, like a clock? We're also going to get the length, local variable, sibling nodes. So by getting the length, we can figure out how many sibling nodes this node has, because we also need that information to calculate where it goes. And we're going to create a couple new variables over here. We're going to create a regular variable and call it nodes location map. Change it to name, make it a map, and change the second variable to vector. Drag it up to the node generation category, compile, control left click, hit drag it in, and do a find. And we're going to find the parent node. Let's actually change the name to nodes info map. And we're going to make a local variable off this, call it parent node info. And the idea behind this is that when we procedurally generate a node on the graph, we're going to store it in this map so that when we iteratively call this function, it's easy retrieval. We'll have all this information about the parent node, and it'll be easier for us to figure out where to place its child node. And we can comment these. And if there's no parent found, that means it's the base node. So we're going to set some values for what we want the base node to have. The node index will be 0. The sibling nodes will be 1 because there will be 1 in the group, the base node. And we're going to alt drag this local parent node info into the graph. Right click here, split struct. And now essentially what we're doing is we're packing data. So we want to decide what each of these floats will mean. We're going to put it in the description so we don't forget, so we can just look back there. X is going to equal degree start, Y is going to equal degree span, and Z is going to equal node tier. And just to briefly explain this, degree start will be the starting degrees of this sort of pie slice of where the parent will be procedurally spawning, going out radially. The degree span will be how many degrees that covers in that pie slice. And the node tier will be essentially how far out from the center it is. Is it in the first group out from the center, the second group out from the center, etc. So if this is the base node, we're going to change the degree span to 360 and the node tier to -1. And let's comment this. Let's drag this down and we'll add a sequence. Now to determine where a node that we're trying to spawn will go on this skill tree, we need to get this parent node info, its parent node's info, and do some math on it. So essentially now what we want to do down here is determine a node's placement information packed into this variable here based on its parent node's placement information, and then use that node's placement information to decide where to spawn it on the skill tree. So the first thing we'll do is set the node info, and we're going to create another variable which is a duplicate of this, the parent node info. So we can just duplicate it and just change its name to node info. Has the same packed values. And we're going to alt left click, drag it out here. And once we figure out what those values are, we're going to add them to our nodes info map. Because remember, this is an iterative function. So when this node that we're calculating now is the parent node in the future, when we're looking up its child nodes, this can be in this map for easy access. We're going to right click and split this side, and now we need to pack this data. We need to determine this node's degree start, degree span, and node tier. We'll do that by getting the parent node info, split, drag off its degree span, safe divide, and this just means if it's divided by 0, the game won't crash. Get the sibling nodes, plug it in, multiply that by the nodes index, copy and paste this over here, add to this, and plug it in here. And so essentially what we're doing here is we're saying that this node's starting radial degree is the same as its parent node's starting radial degree, plus a little extra, depending on which child of the parent it is. Now to get its degree span, copy and paste this, safe divide by sibling nodes. And this degree span basically tells us this is the span of radial degrees that this node's children will be in, should it have any children as well. And calculating its node tier is the easiest. Copy and paste its parent node tier and just add 1 because it's a child of that. It's 1 more in the hierarchy out from the center. And let's comment this. And now that we've saved it to the map for future iterations, we want to use that node info that we just saved to calculate its location on the skill tree, which will output from this function. So drag the return over here. We're going to calculate this node location output now. We'll add a pin to the sequence, come down here, do a reroute, drag in the node info, not the parent node info, this time the node info, split it. We'll do some math to determine where it is. add, divide by 2. And this gives us the node degree from center. Drag off this, get the cosine in degrees, and also the sine in degrees. And from its cosine and sine, we can make a vector 2D, and we can multiply that by splitting this, the z value of this, which is again the node tier. So we're going to multiply that by the node tier times a new float variable that we create called tier distance. Put it in the node generation category. So this tier distance is how far out from the previous tier this next tier is. Let's compile and we'll scroll down, give it a default value of maybe 200. We're going to drag it into the graph. We're going to multiply the tier by the tier distance by this vector. And that is the node location. And we can comment this. So essentially we're doing a little bit of trigonometry to get the node location. So now we're done with this calculate node location function, but for now we can come back over here to the add node branching function. So now we know where we want to add the node. Now we just need to add it. So we'll start by breaking this, move this over here. And we're going to create widget, WBP skill tree node. Right click, promote to local variable, call it node local. And we're going to open up this add widget to nodes canvas function and add some inputs. We'll add a widget input, widget, z order input, integer, alignment input, vector 2D, 2 more vector 2Ds, pivot and position, and lastly an angle input, which is a float. Compile and quickly come back over here to the add node branch and just input node into widget. And let's set some of these values over here. Z order can be 3, just something greater than the other things on the graph, except for if you remember the research points, which we set the Z order to something very high, like 20. The alignment wants to be 0.5, 0.5, and the pivot also 0.5, 0.5. And the position is going to be that calculated node location that we did earlier up here. Now we'll open it back up. Now we'll get the nodes canvas variable that we created over here in the designer. And we'll add child to canvas. Add child to canvas, not add child. And we're going to add this variable here. I'll just do it this way. We'll create a local variable from this canvas slot, set anchors, split this, 0.5 for everything. And this canvas slot we're going to size to content, and we'll also on it set the Z order, and we're going to set the Z order to what we input into the function. So I'll just get the variable here. If you type in get Z order in this list, you're going to see 2. The local variable is always the one under the variables category at the bottom. If you use this one, it'll be the wrong one. So if you want to do it this way, just be careful about that. Set alignment, and we're going to get that alignment that we input. And lastly, set position, and we'll get that position that we input. And now also from that local widget, we'll set the pivot from the pivot input. Again, it's the bottom one. And we'll also set render transform angle, and we'll get that angle that we input. And we're done with this function, so we can close it. Now we're back in the add node branching function. So now that we've created this function, we can reuse it to add other things to the skill tree as well, not just this widget, but other widgets as well, which we'll see later when we create the connector widgets and add those. So now the last thing we want to do is make this function recursive. And the way we do that is we have it call itself when it's done with this operation. So we're going to add a pin to the sequence. Let's comment this, just call it add node. We're going to get that data table, get data table row, get the node, break this to the skill tree node, And now on all of this node's children, we'll run a for each loop and just call this function again. So just drag in the function add node branching, connect array element to node, and connect the parent node to node, because now this child node will become the parent node in the recursive function. And for the parent node location, we can just input the node location that we just calculated. Let's comment it. And the very last thing we need to do is, which we forgot, is set this data table variable to the data table that we created, DT skill tree. And now when we fire up our game and open up the skill tree, we can see that all of our nodes have been procedurally generated. So we have the base node here, we have the 4 nodes in the first tier surrounding it, and we have the 2 nodes coming off of one of those nodes in this first tier. And just as a reminder, if we go back to the data table, you can see we have the base node here, the 4 nodes coming off of the base node as child nodes, and then 2 nodes coming off of one of those nodes over here. So this is data-driven procedural generation. And the really nice thing about this is that now, as we develop and iterate our games and projects, whenever we want to add a new skill, we just come in here and add a row to the data table. We never have to make any visual changes, any design changes. The system just does everything automatically for us. And if we ever want to change the hierarchy of our skill tree, that's easy too. You know, you say URA is a child of UR. We can just delete it and make it a child of something else. And now open up the skill tree and now see it's a child coming off over here. So it's very easy to change and iterate things with the way we're doing it, which will speed up development. Now one quick thing we can do is change the proportion of the node and the text. If you'll remember, when we input the constant into the scale, we only made it 0.2. So it only takes up 20% of the space here. And this was intentional. If we made it 1 or something close to 1, then we couldn't have some of the cool functionality that we have, like the glow, because it would expand out past the perimeter and get clipped. So this is intentional. So what we instead want to do is we want to come over to open up the WBP skill tree node. And in the background here, we can simply scale up the background to maybe something like 5, compile it, and we can come back over to the WBP skill tree and just increase the tier distance. Remember, this is the variable that controls how far spread out the nodes are as they successively create from the parent node. So we'll double the tier distance. And the other thing we can do is come into the node instance and change the look of it. I changed mine to something a little bit simpler. And then when we fire up our game, things look a bit better now. So now we have the basic procedural generation done. In the next video, we'll implement a system to get individual skill information into each node so that it can look different depending on the skill that it represents. So the nodes will no longer see text block, they'll have unique icons and things like that. And moving forward from that point, we'll extend the procedural generation so that we have more options for the look and feel of the tree. As it currently stands, everything just always generates radially in the same way outward from the center. But let's say, for example, we want the base node at the top and we want the branches just going down 180 degrees. Or let's say we want to play with the amount of clumping that the sibling nodes have, or change the degree that the tree begins to spawn nodes at, things like that. We'll add all of these features in. It'll still generate completely procedurally, but we'll add in some nice sliders to control the final look and feel.